Uh, I want to give a disclaimer, and the disclaimer is that I'm not a chemical engineer. So, of course, if there is anyone that is really expert in the hydrogen part and the chemical part of the process that's here, you're more than welcome. But you won't get from me a lot of insights from the chemical engineering perspective. I'm an electronics engineer, and that's the perspective and also the orientation that this webinar has. Also, a lot of the content of this presentation comes from a paper we published a couple of years ago in the magazine. It's already from year 22, and it's related to the use of photovoltaic energy to produce green hydrogen. So a lot of the content of this presentation comes from this paper, and I just want to acknowledge that this has been done also in collaboration with some colleagues. It's not just me. Okay, so the motivation is that we are in the midst of a huge environmental crisis, as 99.9% of the world actually acknowledges, and that we are in climate change, and this is basically a crisis generated by the energy sector. So it's also where the focus of the solution should be, right, in solving the energy problem associated to the emissions of greenhouse gases that cause the climate change. And when we look at the problem, then the sources of greenhouse gas emissions, and this is just to back up the idea that it's a problem that is generated mostly in the energy sector. You can see here that most of the greenhouse gases come from electricity and heat, the industry, transportation, and houses and living. And all these areas are more or less related to energy, particularly fossil fuels burning. While there is another source of greenhouse gas emissions that has to do with agriculture and also other uses of the soils, meat production, and so forth. So most of the greenhouse gas emissions comes from burning of fossil fuels, and this is of course forcing an energy transition. And the energy transition, although this is not the first one we have encountered, we discovered fire, and that was our first energy transition, and that's how we became humans, basically. And then we used the wind, and in Portugal, you use the wind to sail overseas. So those were energy transitions in the past that we know from, and that has been always a good thing for humanity. But this one is a little bit different. So this energy transition is that we have to move away from a very cheap form of energy that we knew how to exploit, which is fossil fuels, and it has become quite challenging to transition, or to envision how to transition even from some industrial sectors that are called hard to abate. So hard to abate applications or hard to abate industrial sectors are those in which transitioning or mitigating the burning of fossil fuels is difficult. So if we look at this chart, which is a way in the IEEE, which is the International Energy Agency, is showing the progress on the technologies for energy transition, and I strongly encourage you to look at those in this link over here. They have like a street light kind of way of following how the technologies are evolving. You can see that there are very few technologies. So only solar photovoltaics, electric vehicles, LED lighting, and some other things that are on track. So these are technologies that are evolving and that are quite on track in relation to how to do energy transition. And then we have some in which more effort is needed and some in which we are not on track. So these are the ones that are really, really difficult, like aviation, heat production, buildings, and so forth, carbon capture, usage, and storage. So these are the ones that are really, really lagging behind. But I wouldn't say that we are very, very good standing with other ones in the mid-tier. For example, international shipping. So all the shipping industry is also quite difficult and lagging a little bit more behind in my view. The same with cooling in buildings and stuff like that. So there is a lot to do. So usually this would be like a very pessimistic view for a normal person, but for engineers, this is basically where the gold is, where we have to dig for gold, right? So all the places where we are lagging behind is actually where engineers should be looking at, because that's where the great opportunities to do some impact are available. And And hydrogen emerges as one of an alternative to use in these hard to abate sectors. Why? Because hydrogen is not really an energy source unless you consider, and we will talk a little bit about later this, there are now some, so they have been founding caverns with hydrogen under the ground. And that could be seen as an energy source, but usually we have to produce hydrogen, so it's an energy carrier. But the good thing, it can be stored and it can be used in mobile applications for that reason. It can be transported, distributed. I wouldn't say really via conventional methods. I mean, it's conventional in the sense it could be pipes, it could be other means of storage and transportation, but this is actually quite challenging. Hydrogen is a very small molecule and it's not easy to store over long periods of time. So it's not as easy to store and to distribute as fossil fuels. But it is still an advantage. Also, hydrogen can be converted back into electricity or to generate heat and from these movements. So hydrogen can be used for a wealth of applications, and that's also very interesting. And one area in which I'm really interested in is that also hydrogen can be converted into chemical energy. So it can be used to produce a gas, synthetic gas, and synthetic fuels. Or these are also usually known as e-fuel or syn fuels, synthetic fuels. And those are very interesting because those won't demand any change to existing infrastructure. So at the end of the day, hydrogen is getting a lot of hype for all these reasons. And depending on how you produce hydrogen, it could be carbon neutral or low in carbon emissions. So not all the forms of producing hydrogen actually are sustainable. And this chart shows how many ways hydrogen can be produced. So the most typical are from steam reforming of natural gas or liquid petrol gas. And this, of course, generates CO2 because it starts from fossil fuels. There is a way of doing carbon capture, and that's a way of producing low carbon hydrogen. And then there is a green hydrogen production versions, which is where you start from the electrolysis of water from any renewable energy source. So it could be concentrated solar power, nuclear PV power, wind power, hydro, and even wave energy. Those could then produce green hydrogen, and you can also have low carbon emission hydrogen produced through nuclear power. Depending on the source of energy, people are now classifying or giving a name based on a color to the way of the hydrogen is produced. So this is usually known as a hydrogen rainbow. You won't find any uniform or standardized way of using these colors, except probably for green and gray hydrogen. But you will see that, for example, in this classification I got from this reference over here, pink hydrogen is referred to the ones that comes from nuclear power, while yellow hydrogen is a hybrid way of producing hydrogen when you're connected to the grid and when the grid has a mixture of green and fossil fuels. And then, depending on the source you read, some people would say yellow hydrogen is when it's made from solar energy and so forth. So take it with a grain of salt. This is no standard and there's no fixed literature about this, but we are going to use this nomenclature over here. So we will refer to green hydrogen when it's electrolysis made from renewable energy sources, and gray when it's natural gas reforming from fossil fuels, natural gas, and so forth. We will refer to yellow hydrogen in this presentation as the one when you are connected to a grid and the grid has a mixed energy origin. Okay? So currently, hydrogen is already being produced. Over 90% of the hydrogen is being produced in a gray form, so from natural gas and liquefied petrol gas. And the application scope of hydrogen today is quite limited. So we use it for refineries, chemical industry, metal and glass processing, and others, like rocket fuel, for example. But a lot is actually used to produce ammonia, and then ammonia is then used for several purposes, among them fertilizers. So as you can see, by the year 2020, there's a growing demand on hydrogen, but of course this is not near a demand of hydrogen would have in energy sector, right? Like as a fuel or energy vector. So in that case, we bring the future uses of hydrogen, or some of them of these are of course already present, but not in mainstream or large scale deployment across the world. But the idea is to use then hydrogen, particularly green hydrogen, to offset emissions in the transport sector, whatever you use it as a fuel cell in electric vehicles and buses, trucks. On maritime applications, we will see at the end of the presentation that not all of these are with fuel cells, so not all of these are actually powered by electricity at the end, but we will see other means of using hydrogen for these applications as well. Also for residential and buildings, like heat and electricity, the production of synthetic fuels like methanol, kerosene, diesel, and maybe I should add here dimethyl ether as well, which is being strongly considered by Germany at this point. And then in the industry sector, in the refining process of several metals and other things, and grid injection of power, so storage as hydrogen to produce electric power and so forth. And here's the projection by IEEE up to the year 2050, and here you can see that the traditional applications of hydrogen will remain as is, but all this over here are the new demand that is projected for the next years in using synfuels, in use for ammonia, the use in power systems, transportation, and so forth. So this is really what's interesting. If this projection becomes true, then this really could be considered a success story, and that hydrogen is helping to mitigate the fossil fuel emissions. So an interesting aspect, I like this flow chart of how the hydrogen economy is linked among each other from the production to the end use, particularly considering the green hydrogen case. So if we're talking about green hydrogen today, I mentioned several options, but the most promising are from a cost perspective to do it from wind and from solar energy. And then you use the electrical energy through electrolysis to produce hydrogen. And then you can use this hydrogen and you can ship it with ships, trucks, pipelines, and store it in tanks. And then you can use hydrogen in the steel industry, chemical industries, and also you can use the hydrogen as fuel cells in transportation and stuff like that. But that's one part of the story of the economy of hydrogen. The other thing would be to use this hydrogen, mix it with CO2, so you capture CO2. So this is CO2 that can be captured freely available, or from processes that are very intensive in producing CO2. And then when you mix those two, you produce methanol. And then methanol is already another form of fuel that it's easier to store, transport, and so forth. And you can also refine methanol into other forms of fuels. You can make kerosene, you can make diesel, and so forth. And those can use all the existing infrastructure, so you won't have to change anything here to transport those forms of fuel. And in those cases, then that would be the drop over here. So you follow the graph, so this drop would be, then you can use it in shipping, aviation, cars, without any change. So you don't have to change your planes, you don't have to change your ships, you don't have to change the infrastructure at the airports and harbors, and etc. So that is also a compelling case of the use of hydrogen. And then you can mix also hydrogen with nitrogen, and then you generate ammonia. And ammonia, if produced this way, it's called green ammonia because it's based on green hydrogen. And then ammonia can be also used for combustion. Ammonia can be used, for example, just for transportation of hydrogen because it's more energy dense and easier to transport and to store. So you can transport ammonia, and then you can at the other side of the shipping, you could take the nitrogen out and you end up again with hydrogen. So you can use the ammonia also as a transportation vector. But you can use it also for combustion and for other applications of ammonia, let's say for fertilizers. So there are many, many ways of in which the hydrogen can find pathways into decarbonizing industry and sectors and become cost effective. But a very interesting part of this presentation, and now you can really realize it in this slide over here, is that if you look, even if you don't consider that some of the end users also use power electronics, right? But if you just consider every molecule of hydrogen that you would use in any of these forms, all those molecules of hydrogen had to pass at the beginning of the stage over many, many power electronics interfaces. So the PV system, the wind turbine goes through power electronics to produce electricity, and then the electrolyzer is powered also by power electronics. So each and every molecule that will be used in the future in this way, whether if it's in hydrogen, nitrogen, or e-fuel form, it has to go through power electronics. And this is why I chose for the title of this presentation, the critical role of power electronics, because this is going to, if everything goes as according to plan, this will be critical infrastructure. So this will be energy critical infrastructure, and all the infrastructure will go and pass, all the power go and will pass through power electronics. So that makes now power electronics not an enabling technology for this application. It's the critical technology. It cannot fail. We cannot afford to have availability ratings or failure ratings of this technology that are high failure ratings. So we cannot afford to have converters failing every 5 years, or having 8% of a power plant down because of failing PV inverters and so forth, because it's going to be part of the critical infrastructure. I will show you later on why it's even more critical than we think at this point, and it has to do with cost as well. So if we look at the economics a little bit now, you can see that green hydrogen at this moment is more expensive than the other ways of producing hydrogen, particularly gray hydrogen, which is no surprise because, of course, reforming of natural gas is more inexpensive than all these power conversion stages and electrolyzers and so forth. It has to do a little bit more with the technology and the level of deployment and large-scale production of the technology, rather than the cost of the energy source. But you can see that projections show that by 2030 and 2050 there will be already an overlap between how cheap, between the prices of green hydrogen and other means of producing hydrogen. And so what we need in order to have a cost-effective hydrogen is that we need to have it below $1.5 the kilogram of hydrogen. And these are the areas in which the energy mix between wind and PV in the world could reach by 2030 this target of cost. So 2030 is not so far away. And there are quite a lot of regions in the world in which we could reach energy sources in which hydrogen could become cost effective. Here you can see why in Chile in particular, where I am from, we are very, very interested in hydrogen because we have a very cheap means of production of solar energy, and the same in some other places in the world where they are highly interested in this, particularly in the Middle East, because they have also very good solar irradiance and will have a cheap production of hydrogen, but also they have all the infrastructure of the petrochemical industry already in place. So if they can go into e-fuels, synfuels very easily, then they even don't have to change anything of the rest of their infrastructure and also chain of logistics, right? So here is the last chart I bring related to cost. So in the squares you will see the actual cost by 2020, and with the circle you will see the projection for 2050. So you can see that all the projections are showing that there will be a strong cost reduction by 2050. And then in yellow, it's solar PV, and in blue is wind offshore, and then in light blue, it's wind onshore. So here you can see that many countries, particularly China, Chile, Middle East, will thrive on solar PV-based hydrogen, and then there are some other economies that could, for example, Europe has a little bit more on offshore wind as advantages over there. And as you can see, all this, the whole point of this is to reach the $1 the kilogram of hydrogen. So all these, the ones that are below this line would be in a good position to take advantage of green hydrogen economy. Okay, so now let's get into the hydrogen basics. So to produce green hydrogen, we do water electrolysis, and water electrolysis it's basically running a DC current through an anode and a cathode, and then having the water split by the electricity, and then the water molecule splits into hydrogen and oxygen, and depending on the construction or the technology, you will have a different kind of ion that goes through a membrane, and it's a slightly different chemical reaction, but at the end of the day, you end up with a hydrogen and oxygen. So the three main technologies that are nowadays being considered are alkaline electrolyzers, also polymer electrolyte and membrane electrolyzers, or PEM, and the solid oxide electrolyzers, or SOE. Now, the ones that are commercialized right now are the first two, solid oxide electrolyzers, although you can find some commercial examples of these ones. These are not large-scale deployed around the world and not mainstream. The main reason for this is because they have to operate at high temperature, and the membrane is quite brittle and fails after some months of uses, and so it is still technology under development, but it could bring a lot of advantages if some of those problems are solved in the future, because this is very efficient. So alkaline electrolyzers, they transport a hydroxide ion, while the PEM, they transport a hydrogen ion, while the solid oxide, of course, has an oxygen ion going through the membrane. The advantages of the alkaline electrolyzer, that this is more established technology, more mature technology, and also more, it's less, not so expensive. PEM electrolyzers are a little bit more expensive. They use more sophisticated materials in their construction that makes them more expensive, but they tend to be also more efficient, and they operate better with variable power than alkaline electrolyzers, making them very interesting solution for green hydrogen production, because you would have fluctuating power of the wind and the solar energy, and that works a little bit better with PEM. So alkaline electrolyzers would be better for yellow hydrogen production, because then you have a steady flow of power. It comes from the grid, and then it will be as green as your grid is. So if you have a very green grid, because you have a lot of hydro, a lot of wind and solar in the grid, then alkaline electrolyzers could be a very interesting alternative, at least in the short term. So if we go into the chemical reactions, though, because the ion that travels through the membrane is different, they operate on a different principle. So the cathode reactions are written over here, and then you see the carrier, the ion that goes through the membrane over here. But at the end, if you see, the total reaction is basically splitting water into hydrogen and half of a molecule of oxygen, or if you want to have the correct chemical equation, 2 molecules of hydrogen of water will produce 2 molecules of hydrogen and 1 of oxygen. So the correct chemical reaction would be 2 molecules here, so you don't end up with a half of a molecule of oxygen, right? But at the end of the day, they all produce exactly the same. If we look now into the construction, the typical construction of an alkaline electrolyzer it's basically a sandwich, a stack of the different parts of the different electrodes, so the anode, the cathode, and with the membrane in the middle. You have holes in which the hydrogen and the oxygen are transported through the stack. So those are these two over here. And then all this the things that here you see around the gasket ring is just because to compress the whole sandwich, and so it won't have leaks and get apart. So it's very easy to build. There are no very complicated materials. They are, of course, very heavy because a lot of metal goes into this. So this is also why transporting this across overseas, let's say making them in China and transporting them all across the world, could be not such a good business model. This falls more into the category as transformers, right? So if you look into the electrical transformer business, because it's a lot of iron and copper, it's very heavy, usually transformers are made locally. So that's why you can see that they're always like local producers or manufacturers of transformers. So maybe in the future, this is not a bad thing. This means that maybe it could also provide fabrication opportunities at the local level. Maybe the membranes could be imported and made in a single place, let's say Europe, US, China, which are the ones looking into this, but the electrolyzers could be made globally. If we look into the PEM, electrolyzer construction is a little bit more sophisticated. You need a distribution plate that is more sophisticated as well to carry water and gases. But basically, there's and also some of the elements in this construction also have some more sophisticated metals than in the previous case, making it a little bit more expensive. Nevertheless, both technologies are quite mature. You can find a lot of providers online. There are quite a few manufacturers, though, that really can make large-scale electrolyzers for large-scale plants. So if you want to build a big hydrogen plant tomorrow, you won't find many providers that can actually produce the amount of electrolyzers at the large scale that you need right now. So there are hundreds of companies that produce electrolyzers, but I will show you later on in the market survey we did, many of those, have 3D renders. They say they build electrolyzers. They might have prototypes as well. They might have sold some few units, but it's not large-scale mature deployment of technology yet. Okay. So here's just an example of alkaline electrolyzer. Here you can see the big cylinder of the stack, and here you can see the PEM, which is more modular in the sense that these are multi-stacks, so that are arranged in the container. So here you can see that also the containers have a lot of empty space. This is also an explanation why it's not. If you have to put a lot of empty space in containers and ship them around the world, that also has a toll on the cost, right? So there is a lot of room for improvement still in terms of cost reduction. And this is what I show you over here. So this is a cost breakdown, the total installed cost of the alkaline technology versus the PEM technology. And here you can see that because the stack, which is the orange part, is more expensive in the PEM solution, you can and basically the power electronics is basically the same cost, but it is from a percentage point of view, it's 25% of the cost in the alkaline electrolyzer, is 20% of the cost in the PEM electrolyzer, just because the cell is the most expensive part of the electrolyzer. So these are based on a total installed cost of 1,400 euro per kilowatt of power and 1,800 euro per kilowatt of power for PEM versus alkaline solution. Here again, you can see why the title of this presentation is the critical role of power electronics, because it's from 25 to 20% of the cost of the electrolyzer is power electronics. So it is a critical technology in this solution, and anything that can be done into reducing the cost of the power electronics part is interesting. And that goes in many ways, right? Not just the cost of the topology and the converter itself, but also maintenance and also reducing the failure rate, increasing reliability and availability of the converter, so that you don't have to do a lot of maintenance and stuff like that. So that's also impacting the cost of the system, and also the volume and weight because of the container and transportation costs. I will talk a little bit more about this later when I give a brief overview of what happened in the PV industry, in the photovoltaic industry, in relation to volume and weight as well, and how maybe that could also relate to some of the improvements that could be done in power electronics. So if we are going to make green hydrogen, let's say from any renewable source, here I'm just showing photovoltaic energy, but this could also be a wind turbine. In that case, you would have here an AC, DC, DC, AC converter instead of a DC, 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 AC, but you get the point. So if you're going to have your electrolyzer connected to an AC grid, the whole power, the path of the power flows through a lot of conversion stages. So you will have in the photovoltaic part maybe one or two, because sometimes the DC-DC is optional, but most of the new power plants have two. So you have 2 stages of PV conversion. In the best cases, you would have 1% losses here, 2% losses here. Then you have a transformer to step up the voltage. Again, another percentage of losses over here. Then you would have transmission, distribution, substation again, to step down the voltage, then a rectifier, and then a DC-DC converter for the regulation of the current to the electrolyzer as well. So if you add up all the losses, of course, there's a lot of losses in between. Since the electrolyzer uses DC current, usually at low voltage, then it bears the question, is the AC coupling the best solution? Could we, instead of that, do DC coupling and produce directly connected to the PV system, let's say? We will talk about this a little bit later, but let's keep for the moment visiting the area of AC coupling, because this is the area that it's actually currently being under deployment in most of the green hydrogen production projects. So the survey I mentioned to you earlier shows here, and bear in mind, this survey was done in 2022, so some things may have changed in the last 3 years, but I don't think that the main conclusion has changed, which is that you can see that there are a lot of electrolyzers and production in the kilowatt area, very small ones over here, and then here you get to 100 kVA, and then there are very few the manufacturers, let's say Siemens, Cummins, and others, that are in the range between 5 and 20 MVA. So if you go to large-scale hydrogen production, you will see quite a few companies being able to provide those, and then you will see a lot of companies doing stuff, either PEM or alkaline electrolyzers in lower power ranges. Another interesting thing is to see that the nominal voltage of the stacks are usually very low, so around 100 to 200. So you can stack those, you can put those stacks in series, and then you can get into a little bit higher voltages. So currently the goal of the industry is to go into 500, 600 territory. So they want to step up the voltage a little bit of the stacks. That means make the stacks larger, or you put stacks in series, right? The whole point for that is to reduce losses. And then you can see also that there are quite a lot of solutions that are single phase or 3-phase, and then some of them with medium voltage connection capability already. So which are the topologies that are used to connect electrolyzers to an AC grid? So most of the topologies are, because these are high in current, low in voltage, usually you have a step-down transformer like this one. So you go from medium voltage to low voltage over here. Usually then you put those in parallel because you need more currents. And a typical converter used is the thyristor-based rectifier. So in this case is a 12-pulse thyristor-based rectifier. And you can also find of more pulses as well, 18 and 24 and so forth. All of them with the secondaries in parallel to increase current, right? But of course, these ones have very poor quality, power quality at the grid side. So here you end up using filters, unless you use transformers that have a lot of pulses, like over 24 pulses. And then there are other solutions based on diode bridge rectifiers, followed by power electronics that can perform any form of power factor correction. These usually have open-end windings over here in order to be able to do the power factor correction. And then you have fully controlled rectifiers that are capable of having very good power quality at the input, like the voltage source converter. Usually those are connected in parallel as well, so in interleaved operation in order to increase the current to going into the electrolyzer. But basically rectifiers, AC-DC rectifiers. Some solutions have a DC-DC stage here in between to adapt the voltages, maybe to step down the voltage a little bit, to buck the voltage from the DC link, and also to provide an extra layer of regulation for the current going into the electrolyzer. And then if we look into DC coupling, so DC coupling, this would be either standalone, not connected to any grid, or connected to a microgrid, a DC microgrid like the ones you are seeing over here. So DC coupling could be done directly connecting PV systems directly to the electrolyzer through a DC-DC converter that performs in part the MPPT of the PV system and in part the regulation of the current going to the rectifier, into the electrolyzer. This one is without galvanic isolation. This one is with galvanic isolation. And then there is a more sophisticated way in doing this in two stages. One converter dedicated to the PV system, one converter dedicated to the electrolyzer. So this can step up. So you have a higher DC bus voltage to reduce losses between the PV system and the electrolyzer. And then you have a step down DC-DC converter that also produces the regulation for the current going to the electrolyzer. So this allows you a higher voltage, even up to medium voltage DC bus, let's say over 1.5 kilovolts of DC bus. And then some options are even the addition of energy storage connected to the DC bus. This is, of course, not bulk energy storage. The whole point of producing hydrogen is to store the PV power into hydrogen, not in a battery. The whole point of this battery, and also could be a supercap instead of a battery, is just to produce regulation of the voltage in this DC bus, so it doesn't fluctuate when you have fluctuations of power at the PV side, let's say because of partial shading or because of clouds or whatever. So you don't pass the fluctuations of power from the PV system to the electrolyzer, so it's absorbed by the energy storage. So kind of a power smoothing idea. The whole point of this is because the electrolyzer, they don't like to, in order to extend the life cycle of the electrolyzer, they don't like to have large power fluctuations and ripples and stuff like that. So that's the purpose of this storage over here. Again, now if you replace this with wind turbine, the wind turbine could have, of course, the wind turbine works with generators. You have an AC-DC converter, and then you could connect directly to the DC bus. But usually wind turbines are very tall and very large. So if you have a wind farm and you want to connect this to a single DC bus, you will have very long DC cables operating at quite low voltage. So in that case, maybe it would be better to have the wind turbine going through AC, DC, DC, AC, then a transformer, then have an AC grid, and then step down the voltage and then have a AC-DC rectifier. Or use some people are also putting forward the idea of using solid state DC-DC converters to being able to operate DC buses at even higher voltages. And that could be a solution, so you can connect your wind turbines at the DC bus and not through an AC bus. So if we look into, we did a survey on different topologies proposed for the DC-DC stages in this kind of applications. These are available in the paper I showed you at the beginning. I won't go into detail of each one. We certainly do a little bit this analysis in the paper, but there are basically two solutions without galvanic isolation, which is the one I mentioned at the beginning. And here you have the interleaved buck converter, and then you have other interleaved topologies. You have partial power converters as well. You have a lot of proposals on these kinds of topologies. So here you might see a transformer. You would think this has isolation, but this is more like a DC-DC auto transformer because there is a current path directly linked between the input and output. So this is not really galvanically isolated. It's a partial power converter. And then you have the isolated solutions. These have galvanic isolation between the input and the output. Here you have the push-pull converter and the full bridge converter. also based on multi-level converters, like this one is the NPC and so forth. So there are also a lot of solutions available nowadays proposed for this kind of application. So the transformer gives you an additional degree of freedom of changing the voltages. So this could be interesting for, let's say, for example, for this approach over here, in which if you have galvanic isolation over here and here as well, then you can have a larger DC bus voltage, and then you can use the transformer turn ratio to step down, right? So that could also be the function of this galvanic isolation. There is no standard related if you need or don't, if you're required or not required to have galvanic isolation. There are some people that have concerns about possible leakage currents that could damage parts of the electrolyzer, the membrane, and so forth, and that could be mitigated through having galvanic isolation. Some people say because it's not grid connected, you won't have any problem. So you don't need actually the galvanic isolation. Plus, these are DC voltages, not AC, so you will have inherently lower common mode voltages and stuff like that. So there is still not a clear path on which of the two solutions would dominate. Of course, doing without isolation is cheaper, and also you get rid of the magnetic components and losses and high frequency switching and so forth. So if solutions could actually be proven to be very effective in this way, I think this could be the solution moving forward. In our group, we have been working on some technologies related to partial power converters. So we have done partial power converters as a pre-regulator for the PV system. So we use this one to do MPPT, and then we use a DCX converter, which is basically galvanic isolation without any control, no regulation whatsoever, just to produce the difference in voltages we need between the input and the output. And this is just to have a higher DC bus, so to reduce losses, right? And then here we have the model of the electrolyzer that we use in this work. This is the actual prototype we built in the lab. We reached 98.6% of efficiency from input to output with this kind of converter, which is very high compared of doing, going the whole AC coupling stuff I showed you at the beginning. Then we have also looked into other topologies. We have been working with the interleave dual buck converter. The advantage of this converter is that we can produce zero current ripple at the output. So one of the things like I mentioned you before that can extend the lifespan of the electrolyzer is to have lower ripples over here in the current. So you can achieve that inherently by having interleaved operation of DC-DC converters, because the interleaved connection will reduce the ripple. But in this case, we can actually find operating points of these converters in which we can work in these points over here where the ripple is completely zero. So here you can see actually the currents going through all the inductors, and here is the sum of the currents of all the inductors. So that's the current actually going to the electrolyzer. And here you can see it's completely continuous current, no ripple whatsoever. Now, in a previous seminar, I presented the solution. There was a chemical guy in the audience, and he told us, it's true we need less ripple. That's fantastic. That's good for the electrolyzer, but we don't want zero ripple. We need a little bit of ripple. And the reason, according to him, was that if you don't have any ripple whatsoever in the current going in through the cathode to the anode, from the anode to the cathode, then the problem is that the bubbles of hydrogen that are formed at the other side will not detach from the membrane, and then it will be more difficult so you will have parts of the membrane that are actually not doing anything at a given point. So we need to actually inject a little bit of ripple. So the good thing of this modulation system is that we can actually set the ripple we want. So we can actually set a line here, and we can, instead of operating where the ripple would be naturally given by the duty cycle, we can actually select at which duty cycle to work to have the desired ripple we want, which is the case I'm showing over here. And you can have a fixed ripple by even modulating between the duty cycles. So if you want a different operating range in which you, let's say, are operating over here, you can have in average this point of operation by doing kind of like an average between two different setting points. And this is how we control it. So basically we control the currents in each of these inductors, and then we leave 1 degree of freedom to control the voltages in these two capacitors over here. So we don't have any unbalance between these two capacitor voltages. So going back to the point of photovoltaic hydrogen production, or rather than that, let's look into the photovoltaic story and how we transitioned from from very large scale grid connected PV inverters into more modular systems, and reflect on if this might be the case also that will happen for hydrogen or not. So this is basically a brain teaser. Some people think it's one thing, some people think it's the other. I will just expose the challenge, and then you can make your own conclusions and even do research on to see which is the way it will go. So of course we have been experimenting a huge growth in photovoltaic energy, I guess in Portugal, you as well. This is the typical PV system connected to the grid, right? So 2 stages. But initially, most of the PV systems were done with this kind of converter, so very large scale grid-tied inverters. You need a crane to hoist to bring this to your PV plant. I mean a truck, and then a crane to put it in place. And then whenever one of these has a failure, you can end up with 1 megawatt, if it's 1 megawatt inverter, up to even 3 megawatts. Today there are large-scale inverters that are 3 megawatt in power, that is down. So we have some PV plants in Chile actually that have this kind of centralized PV inverters, and in some of them 8% are down, and so for in failure, right? So for a 100 megawatt plant, sometimes they have 8%, 8 megawatt not available. So the Chinese, particularly Huawei and Sungrow, they detected this issue, and instead of doing centralized huge inverters and having economy of scale in making bigger and more efficient inverters, they went into the multi-string and string solution, which is making it more modular. But the problem by doing it more modular is that you end up with a higher cost per kilowatt for the same amount of power. So if you do a 1 megawatt here and you do 10 units of 100 kilowatt here, this one is more expensive. But they actually broke a little bit the system, or changed the paradigm by doing a higher power density. And by doing higher power density, they could cut some costs in transportation, and also particularly installation and service. So you don't need, again, you don't need a truck, you don't need a crane. You just can go with a golf cart, 2 people install this stuff. If one goes down because of a failure, you end up only with 100 kilowatts of your system, and you can just change it and you service it offline. So you don't have to bring technicians over to repair this stuff over here and maybe wait a week. You just pull this one out, put a new one in, and then the one that's under failure condition, you can replace offline. And you just keep a couple of spare ones just to being replacing. So the availability of the PV plant is almost 100%. And that's really what broke the system and changed the paradigm. And this is how you can see here is an example from Sungrow. You can see very high power dense converters. So 125 kilowatt in just 60 kilograms, and 30 kilowatts in 100 kilograms. So very high power dense converters in an application that had no power density needs, right? This is not like converters in a car where you need them to be very dense. So that's not the case, right? So they really broke the system this way, and this is how Huawei here and Sungrow have more than 40% of the market by modularizing the technology. So this bears now the question, what will happen for hydrogen? Are we going into this big, yes, sorry. Are we going to these big electrolyzers, big containers that if, part of the cooling system fails, everything has to shut down, and you have a lot of empty space in these containers and a lot of logistics to install those, or going into the more modular approach in which you have smaller system, and then basically instead of having large cables, you have pipes that conduct hydrogen into instead of cables, right? So changing pipes for cables, or cables for pipes, I should say. So I've talked to people from the hydrogen industry. So most of the manufacturers of electrolyzers are in this. They are looking into this approach because, of course, they are looking at the solution as a chemical and mechanical engineers. So the chemical engineers, the electrolyzers, and the mechanical engineers, all the pipes and valves and compressors and stuff like that. But there is a case in point to make in terms of doing more modular approach. So the future will tell, and there are some reasons that are strong in favor of one or the other. But that, like with technology, sometimes some breakthroughs in technologies can enable one solution more than the other. So future will tell. So I will spend the last couple of minutes of my presentation just to show you why it's going to be so critical, the role of power electronics in the future. But because nowadays we see power electronics in lots of applications, motor drives in industry, in our cell phones, charge batteries in cars and stuff like that, and PV systems and wind turbines. But we really could have now power electronics in the whole value chain that currently is in the fossil fuel industry. And I will show you for that the application uses of hydrogen, not just as fuel cell, because most of you think of using hydrogen in an electric vehicle to produce electricity, or in a bus to produce electricity, and then power an electric motor through a fuel cell. But there is also hydrogen combustion, and this doesn't mean then that this application has no power electronics, because of course combustion has no power electronics, but the production of hydrogen does. So we still are part of the chain. So we will, if this one prevails instead of fuel cell, let's say, we still are part of the whole chain of production of the hydrogen that goes into this combustion. The same with green ammonia, and even more with e-fuels. So I will show you some examples in the maritime industry. This is based on a fuel cell. So people are thinking of using fuel cells for maritime applications, but just for short distances. So for small vessels below 2,000 nautical miles, that would be the range. That's the sweet spot for fuel cells in the case of maritime applications. If we look into hydrogen combustion, this would be where we need a little bit more of power. There are some solutions already being developed by, this one is a solution between a Belgian company and a Spanish company, I believe, where they are doing hydrogen combustion. So now this motor here combusts hydrogen to produce the movement. But again, we still are here in this and the previous solution. We need to bring hydrogen on board with tanks, like hydrogen storage tanks. And hydrogen, it's also only powered energy dense if you really compress it hard. And also it's that you will have to change all the logistics of the harbor in order to do so. Other people are pushing into the idea of using green ammonia. So producing hydrogen, capturing nitrogen, and then mixing hydrogen with nitrogen to produce ammonia, and then using combustion of ammonia. So this is a combustion engine in which we will combust ammonia. Actually, this is a dual engine. You can combust here diesel, or you can combust ammonia. So if you produce a ship that has this engine, you can combust in the meantime diesel, and then when the green ammonia is already available, then you just switch to the other one without doing anything to the machine. The problem with ammonia is that it generates some toxic waste. That's the problem with ammonia. The good thing is that it's easier to store and transport compared to hydrogen. So even some people are thinking of using ammonia as a means of transportation of hydrogen. And then when you arrive at the other place, at your harbor, then you go from ammonia back to hydrogen, right? And then there is the people that are making the case of e-fuels. So they say, no, don't change anything of the machine, of the ships. Don't change anything of the harbors, anything of the logistics on the harbor. We just are going to change the way we produce fuel. Instead of mining fossil fuels, we will produce e-fuels, synthetic fuels from hydrogen. So mix hydrogen with CO2 to produce methanol, and then use methanol to produce any kind of e-fuel. And then we only have to lower the cost of that, and then we keep all the rest of the technologies as they are. We don't have to change planes, we don't have to change buses and trucks. and ships, we just have to change how we produce the fuel in a synthetic way. If we look into aviation, people are also making the case of using fuel cell in aviation. So here's an example of universal hydrogen. And here you can see actually the big problem of hydrogen. It's the logistics of it. So you will need to have a way of distributing hydrogen. You will have to change all the airports in the world. So not just change the plane technology to fuel cell and an electric motor, but then you will have to change all the airport logistics as well. And this should be deployed across the whole world. And then if you see that we have more than 400,000 planes already working and operating using kerosene and other means of jet fuel, changing all the airports in the world will be very difficult. Not just changing the planes, but then changing the airports and the logistics, and then producing hydrogen and being able to transport and store them in all the airports. If you remember, one of the bad issues with the Airbus A380 was that very few airports in the world could actually land an A380. So the A380 is just a bigger plane. And that was already very difficult to be able to land in many airports in the world. And this is one of the reasons that the A380 only was used from some airports for long-haul flights from one to other airports, but they couldn't fly to many airports in the world. And this is something that could happen also with the aviation industry if we want to change everything to hydrogen. Then this is another example of fuel cell-based hydrogen. This is being done by Airbus. So Airbus is also looking into this, but Airbus is also looking into other solutions as well. And this is a project by Rolls-Royce and EasyJet in which they are going to look into the combustion of hydrogen. So here they use basically a new kind of jet propulsion engine in which they combust hydrogen instead of jet fuel. But in this case, again, you need to change the logistics of the airports as well, and also onboard the aircraft to store hydrogen as well. So the only thing you change here is the fuel cell and the electric motor for a hydrogen combustion engine. And the other way would be to use traditional jet fuel, but only made from e-fuels again. So using the carbon capture to produce methanol and the methanol refined into jet fuel. And then you can use the airplanes as they are, no changes whatsoever. Another non-conventional application people are looking into for green hydrogen is as a replacement for how do you call it? Diesel. How to call it in English? Well, anyway, electrolyzer group to produce electricity when your electricity goes down, right? So backup system. So these are called hydrogen energy storage system. And the whole point here is to have, to produce hydrogen. You can either produce hydrogen from the grid, which is the yellow case, going from the grid through the electrolyzer to produce hydrogen, and then using a fuel cell to produce electricity back again. The other thing is you can have also PV systems on the rooftop of your building and produce also green hydrogen and use that hydrogen to produce electricity back again. The battery is only to use to soften and smoothen the fluctuations in the DC bus. So the good thing of this is that you could produce hydrogen at a very slow rate. So these DC-DC converters over here could be very low in power, and this could be an electrolyzer, which is also low in power, because you will accumulate hydrogen over time, and then you will have, let's say, your storage tank full, and when the electricity goes down and you need this for backup, then this one is the one that needs to be at the rated power. So this could be, let's say, a 20 kilowatt converter if this is for the backup system of a building. And this could also be this has to be 20 kilowatts, so you can actually supply 20 kilowatts to the building, but you don't need to produce hydrogen with 20 kilowatts, right? Because this is going to be backup for, let's say, 2 hours of an outage. And so you just need hydrogen for 2 hours. So this could be really running at below 1 kilowatt of power to produce actually the hydrogen over weeks or months even of time in which you don't have any outage, right? And the e-fuel stuff, the synthetic fuel stuff is also taking off. Really, a lot of people are looking into this. HIF, Highly Innovative Fuel, is a company, was born in Chile, but from the union from Siemens, Porsche, and AME. They make a joint venture to produce highly innovative fuels, to produce synthetic fuels based from hydrogen in the south of Chile. This is in Patagonia, where we had a lot of wind. And the idea is to produce hydrogen here based on wind energy, and then have carbon capture to produce methanol. They have already produced e-diesel, and they have some Porsche cars going on the roads with this diesel made from green synthetic fuels. But they have already powered some World Cups in racing using Porsche Mobile Super Cup, using these e-fuels made in the south of Chile. This company is now based in the US, in Texas, and it's really growing. And there are many other companies looking also into e-fuels, synthetic fuels. And as you can see, this will be a way of producing hydrocarbons, but starting from electricity, and that's why they are called e-fuels. And this is really something, if we can, these ones are now 6 to 8 times more expensive than fossil fuels. But if we can lower the cost of this, we don't have to change the ships, we don't have to change the planes, we don't have to change any of the infrastructure. We can use existing infrastructure. We only have to be able to lower the cost of how we produce synthetic fuels. So the big question is, what's going to be easier, to change all the technology in airplanes and ships and cars and buses and trucks and all the logistics and deploy this around the world, or just in few places where it's going to be really cost effective to produce synthetic fuels, let's say Australia, Chile, the north of Africa, the Middle East, some places in China, the south of Europe, like Portugal and Spain and Italy, and in those places produce synthetic fuels. All of them starting from electricity, all of them going through power electronics. So the takeaways of my presentation are that green hydrogen is emerging as a viable energy carrier for energy transition. The other thing is that it's not yet a mature market. You can see from the market survey that we did that there are not quite a plethora of electrolyzer manufacturers in the world that can deploy large-scale plants at this point. And there is also modular, smaller power systems, and also high power, very large centralized system. That's also showing that it's not yet a very mature market as well. We also a big takeaway is basically that power electronics is going to be a critical technology for the cost-effective production of green hydrogen. I showed you it's 20% to 25% of the cost of an electrolyzer is power electronics. And then you have the maintenance and the availability of the electrolyzer as well, in which power electronics will have an impact. So it's critical to the development of cost-effective green hydrogen. And then we have if you look into the fact that now we could replace fossil fuels with e-fuels that are also going through power electronics. We could say that in the future, if this is actually finally the solution that prevails, is that most of the world energy will go through power electronics and power systems. So, which is not the case right now. So now everything that goes through power electronics and power systems is basically what's grid connected and what's in the utility. But we're now talking of untapping the whole use of fossil fuels also to produce heat in industry, in manufacturing industry, in mining industry, and other industries, and not only just transportation. So if you really look into the fact that we could be producing e-fuels and replacing fossil fuels with this, power electronics and power systems and all the related technologies could be really, really, really critical infrastructure in the future. So that concludes my presentation.